Welcome to Science for Sleep. Tonight, we will explore one of the most extreme and misunderstood events in the universe. We will follow the quiet, inevitable process through which matter collapses so completely that space and time themselves are permanently altered. Tonight, we will trace how a black hole is actually born, not as a sudden cosmic spectacle, but as a slow and precise consequence of gravity, mass, and the limits of nature. This is the story of how stars die, how pressure fails, and how the universe allows regions of space-time to close in on themselves. When most people imagine the birth of a black hole, they picture a violent explosion and a tearing of space or a catastrophic cosmic rupture. In reality, the formation of a black hole is not defined by chaos, but by balance breaking down. It begins quietly, from inside a star that has spent millions of years in a state of fragile equilibrium. For most of its life, a star exists because two immense forces oppose each other perfectly. Gravity pulls inward, attempting to compress the star into a smaller and denser object. At the same time, nuclear fusion in the star's core pushes outward, releasing energy that resists collapse. As long as these forces remain balanced, the star shines steadily, unchanged on human timescales. This balance is not guaranteed forever. It depends entirely on fuel. Inside a star's core, hydrogen atoms fuse into helium, releasing energy that flows outward as heat and light. This energy provides the pressure needed to counter gravity. Over millions or billions of years, that hydrogen supply slowly diminishes. As the fuel changes, so does the nature of the balance holding the star together. What happens next depends on the star's mass, a single property that determines whether a star will fade quietly, explode spectacularly, or collapse into something far more extreme. Small and medium-sized stars, including stars like our Sun, will never become black holes. When their hydrogen runs low, they expand into red giants, shed their outer layers, and leave behind dense remnants known as white dwarfs. These remnants are supported by a quantum mechanical pressure that prevents further collapse. But massive stars follow a very different path. When a star is born with more than about 8 times the mass of the Sun, its fate is sealed from the beginning. Gravity in such stars is relentless, demanding stronger and stronger forms of pressure to keep collapse at bay. And as a massive star ages, its core temperature rises, allowing heavier elements to form. Hydrogen fuses into helium. Helium fuses into carbon. Carbon into oxygen, neon, and magnesium. Eventually, silicon fuses into iron. This sequence is not gradual. Each stage happens faster than the last. While hydrogen burning may last millions of years, silicon burning can be completed in days. The star is racing toward an unavoidable limit, and that limit is iron. Iron is the end of the road for nuclear fusion in stars. Unlike lighter elements, fusing iron does not release energy. It consumes it. When a massive star's core becomes dominated by iron, the engine that has supported the star against gravity shuts down. There is no longer a source of outward pressure strong enough to counter the inward pull of the star's own mass. At this moment, the balance that has existed for millions of years collapses catastrophically. Gravity takes control. The iron core begins to collapse inward at a significant fraction of the speed of light. Atoms are crushed together so tightly that electrons are forced into protons, forming neutrons and releasing floods of neutrinos. In less than a second, the core shrinks from a region larger than Earth to a sphere only tens of kilometers across. The outer layers of the star crash inward, then rebound violently, producing a supernova explosion that can briefly outshine entire galaxies. For some stars, this explosion leaves behind a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons. Neutron stars are supported by neutron degeneracy pressure, another quantum effect that resists further collapse. But this support has limits. If the collapsing core is too massive, even neutron pressure fails. When that happens, there is no known force capable of stopping gravity. This is the moment a black hole is born. When gravity overwhelms all known forms of pressure, collapse continues without interruption. Matter is compressed into an ever smaller volume. Space-time curves more steeply with each passing instant. Eventually, a boundary forms around the collapsing core. This boundary is not a physical surface. It is a geometric threshold in space-time itself. Beyond this threshold, escape becomes impossible. Not because matter is trapped by force, but because all possible paths through space-time lead inward. This boundary is known as the event horizon. Once the event horizon forms, the black hole exists. From the outside, your collapse appears to slow and fade. Signals from the infalling matter become increasingly red-shifted, stretched to longer wavelengths as they climb out of the intense gravitational field. To a distant observer, the formation of the black hole seems to freeze at the horizon, fading into darkness. But for the matter itself, collapse continues. Within the horizon, space-time is so strongly curved that moving forward in time means moving deeper inward. There is no halt, no reversal, no stable state. The black hole's birth is complete, not with an explosion, but with silence. What remains after this process is deceptively simple. A black hole is defined by only a few properties: mass, rotation, and electric charge. All other details about the matter that formed it are erased from the observable universe. The complex structure of the original star, its chemical composition, its internal layers, all vanish behind the horizon. The black hole becomes one of the simplest objects allowed by physics, even though it was formed through one of the most extreme processes imaginable. This simplicity hides extraordinary consequences. A black hole does not simply sit in space like an object. It reshapes the geometry around it. Time slows near it. Space bends inward. Orbits behave differently. Light paths curve dramatically. These effects are not optional features. They are unavoidable consequences of mass compressed beyond a critical limit. The birth of a black hole marks the moment when space-time itself becomes the dominant actor. Matter no longer determines structure. Geometry does. The rules that govern planets, stars, and galaxies give way to rules that govern horizons, singularities, and curvature beyond ordinary experience. Importantly, black holes are not born only from dying stars. There may be other pathways. In the early universe, regions of exceptionally high density may have collapsed directly into black holes, forming primordial black holes without ever becoming stars. These objects, if they exist, would represent fossils from the universe's earliest moments. Their formation would be governed not by stellar death, but by the behavior of space-time itself under extreme conditions shortly after the universe began expanding. There are also theoretical pathways involving the direct collapse of massive gas clouds, bypassing traditional star formation altogether. In certain environments, gas may collapse so rapidly and efficiently that it forms a black hole without ever igniting nuclear fusion. These processes may explain the existence of supermassive black holes found at the centers of galaxies, some of which formed remarkably early in cosmic history. Despite these possibilities, the core principle remains the same. A black hole is born when gravity wins completely. When no pressure, no force, no quantum effect is sufficient to resist collapse. Space-time closes in on itself and forms a region from which nothing can return. This does not mean black holes consume everything around them. They do not grow endlessly by default. Like any object, they exert gravity according to their mass. A black hole with the mass of the Sun would influence its surroundings no more than the Sun itself did, except at extremely close distances. The drama of black holes lies not in their appetite, but in their formation and structure. Understanding how black holes are born requires abandoning familiar intuition. It requires accepting that space and time are not rigid backdrops, but flexible participants in physical processes. It requires recognizing that silence does not mean inactivity, and darkness does not mean emptiness. As we continue, we will move deeper into the mechanics of collapse. We will explore what happens inside a dying star as pressure fails, how quantum effects delay collapse, and why those effects ultimately surrender. We will examine the precise conditions under which neutron stars survive or fail, and how the universe decides whether a collapse ends in stability or in absolute curvature. And this is not a story of destruction alone. It is a story of limits, limits of matter, limits of pressure, limits of physics as we currently understand it. The birth of a black hole marks the point where known laws are pushed to their edge and space-time takes over. To understand how a black hole is actually born, it is necessary to slow the process down and examine collapse moment by moment. The final seconds of a massive star's life are not chaotic in the way explosions are often imagined. They are governed by strict physical rules that unfold with precision. Gravity does not rush. It accelerates methodically as resistance weakens. Every stage of collapse follows inevitably from the failure of the stage before it. At the center of a massive star nearing the end of its life lies an iron core. This core is inert. It produces no energy. Its only role is to respond to forces acting upon it. As fusion halts, thermal pressure drops rapidly. With no outward energy flow to maintain equilibrium, gravity begins compressing the core inward. This compression increases density and temperature. But unlike earlier stages of stellar evolution, the rising temperature no longer helps. There is no fusion reaction capable of igniting within iron to reverse the process. As the core contracts, electrons are forced closer together. Normally, electrons resist compression due to a quantum effect known as electron degeneracy pressure. This pressure arises from the Pauli exclusion principle, which prevents identical fermions from occupying the same quantum state. In white dwarfs, this pressure is sufficient to halt collapse. In massive stellar cores, gravity overwhelms it. When gravity wins, electrons are driven into protons through a process called electron capture. Protons and electrons combine to form neutrons, releasing neutrinos in vast numbers. This transformation radically alters the composition of the core. What was once a plasma of nuclei and electrons becomes a dense sea of neutrons. At the same time, neutrinos escape outward, carrying away energy and further weakening any remaining resistance to collapse. The loss of neutrinos is crucial. They remove pressure support at exactly the moment gravity is strengthening. The core contracts faster. Density rises to values exceeding those found inside atomic nuclei. The star's interior briefly becomes one of the densest environments in the universe, surpassed only by black holes themselves. For a narrow range of masses, neutron degeneracy pressure halts collapse at this point. The core stiffens. The inward motion rebounds. Shock waves propagate outward, aided by neutrino interactions, driving a supernova explosion. A neutron star is born, supported by the same quantum rules that once supported electrons, now applied to neutrons. This outcome is dramatic, but it is not the most extreme. When the mass of the collapsing core exceeds a critical threshold, neutron pressure fails. This threshold is not sharply defined, but it lies at around 2 to 3 times the mass of the Sun. Beyond this point, even the repulsive effects arising from quantum mechanics cannot resist gravity. Neutrons themselves are forced into closer proximity than quantum theory comfortably allows. At this stage, collapse becomes unstoppable. There is no longer a physical mechanism capable of providing outward pressure. The core contracts continuously. Density increases without bound. Space-time curvature becomes extreme. Unlike earlier phases, there is no bounce, no rebound, no shock capable of reversing the motion. The star's core passes a point of no return. This point is not marked by a surface or a physical boundary. It is defined geometrically. As mass collapses into a smaller volume, the escape velocity near the core increases. When this escape velocity reaches the speed of light, a critical threshold is crossed. From that moment onward, no signal traveling at or below the speed of light can escape. This threshold defines the event horizon. The event horizon does not form at the center and expand outward. It forms around the collapsing mass as a whole. From the perspective of the infalling matter, nothing special occurs at the horizon itself. There is no sudden force, no wall, no sensation of crossing a boundary. The laws of physics locally remain the same. The significance of the horizon lies not in what the matter experiences, but in what outside observers can no longer see. To a distant observer, the formation of the horizon appears gradual. Light emitted from the collapsing matter becomes increasingly redshifted. Each signal takes longer to escape. The star appears to freeze in time, dimming and fading. Eventually, it disappears entirely. From the outside, the black hole seems to form asymptotically, never quite completing collapse. From the inside, collapse proceeds uninterrupted. This difference in perspective is not an illusion. It is a direct consequence of how time behaves in strong gravitational fields. Near the forming black hole, time slows dramatically relative to distant observers. This slowing is not subjective. It is measurable and real. Clocks near the collapsing core tick more slowly than clocks far away. As the event horizon forms, this time dilation becomes extreme. Inside the horizon, the structure of space-time changes fundamentally. The roles of space and time exchange in a critical way. Moving inward becomes as inevitable as moving forward in time. Just as no one can stop time from advancing, nothing inside the horizon can stop moving toward the center. Collapse is not a choice or a process that can be halted. It is the future. The endpoint of this collapse is predicted to be a singularity, a region where density and curvature become infinite. At this point, known physical laws cease to provide meaningful predictions. Whether singularities truly exist, or whether new physics intervenes, remains unknown. What is certain is that the black hole's defining features do not depend on the details of this interior region. Everything observable lies outside the horizon. Once the horizon forms, the black hole is complete. It no longer carries information about the structure of the star that created it. It does not retain layers, composition, or complexity. All that remains accessible is its total mass, its rotation, and its electric charge. This reduction of complexity is one of the most profound aspects of black hole physics. Rotation plays a critical role in black hole birth. Most stars rotate, and conservation of angular momentum ensures that collapse dramatically increases rotation speed. As the core contracts, it spins faster. Much like an ice skater pulling in their arms, this rotation affects the shape of the event horizon and the surrounding spacetime. Rapidly rotating black holes develop flattened horizons and exhibit effects such as frame dragging, where spacetime itself is pulled into rotation. In extreme cases, rotation may influence whether collapse proceeds directly to a black hole or temporarily stabilizes as a neutron star. Magnetic fields and rotation can channel energy outward, affecting the dynamics of the supernova explosion. However, these effects do not prevent black hole formation when mass exceeds the critical limit. They may delay it, but gravity ultimately prevails. Not all black holes form through violent stellar deaths. Some may form quietly. In regions of dense gas, especially in the early universe, massive clouds may collapse directly under gravity without fragmenting into stars. These direct collapse black holes may explain how supermassive black holes formed so quickly after the universe began. In these scenarios, collapse proceeds rapidly, bypassing the supernova stage entirely. In such cases, the birth of a black hole may produce little or no electromagnetic radiation. The event horizon forms without fireworks. The universe allows a region of space-time to close in on itself silently, guided solely by mass and gravity. There is also the possibility of primordial black holes, formed not from stars or gas, but from fluctuations in density shortly after the Big Bang. If certain regions were slightly denser than average, gravity may have caused them to collapse directly into black holes. These objects would have formed before stars existed, carrying information about the universe's earliest conditions. Their existence remains speculative, but their formation would follow the same fundamental principle: collapse beyond resistance. Across all these pathways, the rule remains unchanged. A black hole is born when gravity overwhelms every known form of pressure. The details may differ. The timescales may vary. The environment may change. But the underlying mechanism is universal. This universality is what makes black holes such powerful tools for understanding physics. Their birth represents a boundary between the known and the unknown, and it marks the point where classical descriptions of matter fail and geometry dominates. Once a black hole is born, the universe around it does not immediately change in dramatic ways. There is no sudden tearing of space, no sweeping wave of destruction radiating outward. In fact, from a distance, the birth of a black hole can appear deceptively ordinary. The gravitational influence of the newly formed black hole is determined entirely by its mass, not by the violence of its creation. If the collapsing star had the same mass before and after the event, its surroundings feel almost no difference at all. Planets, stars, and gas clouds far away continue their motions uninterrupted, unaware that space-time itself has crossed a fundamental threshold. Yet close to the black hole, everything is different. The region near the event horizon becomes an extreme environment where the familiar rules governing motion, time, and energy no longer behave intuitively. Space bends inward so steeply that paths which once allowed escape now curve back toward the center. Time slows relative to distant observers, stretching moments into near stillness at the horizon. These effects are not temporary. They are permanent features of the geometry created by collapse. The newly formed black hole is not static. It is born in motion, inheriting angular momentum from the star that created it. Even a slowly rotating star can produce a rapidly spinning black hole, because collapse concentrates rotation into a much smaller region. This rotation profoundly affects the surrounding space-time. Instead of space remaining still, it is dragged around the black hole, twisting into a vortex-like structure. This effect, known as frame dragging, forces nearby matter and even light itself to participate in the black hole's rotation. The region just outside the event horizon of a rotating black hole behaves in a particularly strange way. This region, called the ergosphere, is defined not by an inability to escape, but by an inability to remain stationary. Within the ergosphere, space-time is dragged so strongly that no object can remain at rest relative to distant stars. Everything is compelled to move in the direction of the black hole's spin. This region allows energy to be extracted from the black hole's rotation, demonstrating that even after birth, a black hole is not entirely isolated from the universe around it. The formation of the event horizon also marks the moment when information about the collapsing star becomes inaccessible. From the outside, it becomes impossible to determine how the black hole formed by observing its interior. Whether the star rotated rapidly or slowly, whether it contained heavy elements or light ones, whether it collapsed through a supernova or direct collapse, all of these details are erased. This loss of information is not a technological limitation. It is a fundamental feature of black holes. This feature leads to one of the deepest puzzles in modern physics. According to quantum mechanics, information about physical systems cannot be destroyed. According to classical descriptions of black holes, information disappears behind the event horizon, never to be recovered. To reconciling these two principles remains one of the central challenges in theoretical physics. While the solution likely lies in a deeper understanding of quantum gravity, the conflict itself arises directly from how black holes are born. Despite this mystery, black holes do not grow without limit. A newborn black hole's mass is determined by how much matter collapses into it during formation. Additional mass can be gained later, but only if surrounding material falls in. This accretion process is often slow. Gas must lose angular momentum before it can spiral inward. Stars must pass extremely close to be captured. Black holes are not cosmic vacuum cleaners. Their influence is powerful only at short distances. However, when matter does fall toward a black hole, the process can be extraordinarily energetic. Those gas spiraling inward forms an accretion disk, heating up as gravitational energy is converted into heat and radiation. In some cases, magnetic fields channel a fraction of this energy into narrow jets that shoot outward at nearly the speed of light. These jets can extend for thousands of light years, affecting entire galaxies. Ironically, the brightest black holes in the universe are not those that are consuming everything nearby, but those that are surrounded by abundant material that has not yet crossed the horizon. The existence of these energetic phenomena sometimes obscures the quiet truth of black hole birth. The black hole itself emits nothing. The light, heat, and radiation associated with black holes come from matter outside the horizon, struggling against gravity before finally surrendering. The defining moment of black hole formation is invisible by its very nature. Once the horizon forms, direct observation becomes impossible. Newborn black holes can also announce their existence through gravitational waves. When collapse is asymmetric, or when the black hole forms in a binary system, the sudden rearrangement of mass and space-time produces ripples that propagate outward at the speed of light. These gravitational waves carry information about the collapse process itself, offering indirect evidence of black hole birth. Unlike light, these waves pass through matter unimpeded, preserving a record of events that would otherwise remain hidden. In some cases, black holes are born already paired with companions. Binary systems formed from massive stars can produce black hole binaries whose orbits tighten over time. As they orbit, they emit gravitational waves, slowly losing energy and spiraling inward. Eventually, they merge, forming a larger black hole. These mergers are among the most powerful events in the universe, yet they occur without sound or light. Their signals are encoded entirely in space-time itself. The study of these events has transformed understanding of black hole formation. Observations reveal black holes with masses larger than expected from traditional stellar models. This suggests that some black holes grow through repeated mergers or form through direct collapse pathways that bypass ordinary stellar evolution. Each detection refines models of how black holes are born and evolve. Black hole birth is also intimately tied to the evolution of galaxies. Supermassive black holes reside at the centers of most galaxies, including our own. Their masses correlate strongly with the properties of their host galaxies, suggesting a shared history. How these enormous black holes formed so early remains an open question. Direct collapse of massive gas clouds is one leading explanation, but the precise mechanisms are still under investigation. What is clear is that once a black hole forms, it becomes a long-lived feature of the universe. Unlike stars, which exhaust fuel and fade, black holes persist. They lose mass only through extremely slow quantum processes, taking timescales vastly longer than the age of the universe. In practical terms, a black hole, once born, remains. This permanence makes black holes valuable records of cosmic history. Their masses, spins, and distributions reflect the conditions under which they formed. By studying populations of black holes, we scientists can infer the history of star formation, galaxy mergers, and the behavior of matter under extreme conditions. Black hole birth is not just an endpoint. It is a data point in a much larger story. The process of collapse also highlights the limits of current knowledge. Near the center of a black hole, where density and curvature become extreme, existing theories break down. General relativity predicts singularities, but it does not explain their true nature. Quantum mechanics governs the behavior of matter at small scales, but it does not yet incorporate gravity in a complete way. Black hole birth occurs precisely where these theories overlap and conflict. This conflict is not a flaw. It is a guide. It points toward the need for a deeper framework that unifies gravity and quantum mechanics. Black holes serve as natural laboratories for exploring this unification, not because they are accessible, but because they force questions that cannot be ignored. Understanding how black holes are born requires accepting that some answers remain incomplete. The overall process is well described. The details near the center are not. This combination of certainty and uncertainty defines the frontier of modern physics. To understand how black holes are actually born across the universe, it is necessary to distinguish between the different categories of black holes and the specific conditions that lead to their formation. While the fundamental mechanism remains the same, collapse beyond all resistance, the pathways vary depending on mass, environment, and cosmic time. Stellar mass black holes, intermediate mass black holes, and supermassive black holes each represent outcomes shaped by different histories. Yet all are governed by the same underlying physics. Stellar mass black holes are the most common type directly observed. They are born from the deaths of massive stars, typically with masses ranging from a few times that of the Sun to several tens of solar masses. Their formation follows the collapse process already described, driven by the exhaustion of nuclear fuel and the failure of pressure to counter gravity. These black holes populate galaxies in large numbers, scattered throughout disks, halos, and dense star clusters. Each carries within it the memory of a star that once burned brightly and then vanished. The mass of a stellar mass black hole is not determined solely by the mass of the original star, when it is influenced by how much material is lost during the star's life and during the supernova explosion. Powerful stellar winds can strip away outer layers long before collapse begins. Explosive ejection during the supernova can remove additional mass. In some cases, the explosion is weak or fails entirely, allowing much of the star's material to fall back into the forming black hole. This fallback process can significantly increase the black hole's mass creating heavier remnants than expected. Metallicity plays an important role in this process. Stars formed from gas rich in heavy elements tend to lose more mass through stellar winds than those formed from more pristine material. As a result, black holes formed in environments with low metallicity, such as early galaxies or certain regions of the modern universe, can be substantially more massive. Observations of black hole mergers through gravitational waves have revealed populations of unexpectedly heavy black holes supporting this connection. Intermediate mass black holes occupy a more uncertain category. With masses ranging from hundreds to hundreds of thousands of times that of the Sun, they bridge the gap between stellar remnants and supermassive black holes. Their existence was long debated, but growing evidence suggests they do exist, particularly in dense star clusters. Their formation pathways are still under investigation, but several possibilities have emerged. One likely pathway involves repeated mergers of stellar mass black holes within dense environments. In globular clusters, where stars and remnants are packed closely together, gravitational interactions can cause black holes to sink toward the center. There, they may form binaries, merge, and grow in mass. Over time, this process can build progressively larger black holes. Another possibility involves the collapse of exceptionally massive stars formed through stellar collisions or mergers early in a cluster's life. These stars may collapse directly into intermediate mass black holes without fragmenting. Direct collapse of massive gas clouds may also produce intermediate mass black holes under certain conditions. If gas collapses rapidly without forming many stars, gravity may concentrate enough mass into a compact region to form a black hole directly. These scenarios highlight the importance of environment in shaping black hole birth. Density, composition, and dynamics all influence outcomes. Supermassive black holes represent the most extreme outcome of collapse. Found at the centers of galaxies, they possess masses millions to billions of times that of the Sun. Their existence poses one of the most challenging questions in astrophysics. How did such massive objects form so early in the universe's history? Observations reveal supermassive black holes already in place when the universe was less than 1 billion years old, leaving little time for gradual growth through ordinary accretion. One proposed solution is direct collapse. In the early universe, large reservoirs of pristine gas may have collapsed rapidly under gravity, forming massive black hole seeds without first forming stars. These seeds, already thousands or tens of thousands of solar masses, could then grow quickly through accretion and mergers. This process requires specific conditions, including suppression of cooling and fragmentation, which may have been more common in the early universe. Another pathway involves rapid growth from smaller seeds. Stellar mass black holes formed from the first generation of stars may have accreted gas at near the maximum possible rate, growing exponentially. Repeated mergers between black holes during galaxy assembly could further accelerate growth. While this pathway faces challenges related to timescales and feedback, it may contribute alongside direct collapse. Regardless of pathway, the formation of supermassive black holes demonstrates that gravity can organize matter on extraordinary scales. These objects influence the evolution of entire galaxies. Their growth releases enormous amounts of energy, regulating star formation and shaping galactic structure. In this sense, black hole birth is not an isolated event, but a central driver of cosmic evolution. The early universe provided conditions unlike those seen today. Higher densities, abundant gas, and frequent interactions created fertile ground for black hole formation. As the universe expanded and cooled, these conditions became rarer, altering the dominant pathways of black hole birth. Studying black holes across cosmic time reveals this transition, offering insight into how the universe itself evolved. Black hole birth is also influenced by randomness. Small differences in initial conditions can lead to different outcomes. A star just below a critical mass may leave behind a neutron star, while a slightly heavier one becomes a black hole. Variations in rotation, magnetic fields, and environment further complicate predictions. This sensitivity underscores the probabilistic nature of astrophysical processes. Despite this complexity, the defining feature of black hole birth remains clear. It occurs when matter is compressed beyond a threshold where no known force can resist gravity. This threshold does not depend on composition or history. It is a universal limit imposed by the structure of space-time itself. Understanding this limit has practical implications beyond astrophysics. It informs theories of matter at extreme densities, guides searches for new physics, and shapes interpretations of gravitational wave data. Each black hole detected carries information about the conditions that produced it, encoded in its mass and spin. As observations improve, the population of known black holes grows. Moss patterns emerge. Distributions of mass and spin reveal preferred formation channels. Outliers challenge existing models. This dialogue between observation and theory refines understanding of how black holes are born. The birth of a black hole is therefore not a singular phenomenon, but a spectrum of processes unified by a single principle. Gravity, when unopposed, reshapes space-time irreversibly. The universe allows regions to collapse so completely that they become hidden behind horizons, influencing everything around them while revealing nothing of their interiors. In the next section, we will examine the role of time during black hole formation. We will explore how different observers experience collapse differently, how time dilation shapes observation, and how the birth of a black hole challenges intuitive notions of simultaneity and sequence. The role of time during the birth of a black hole is one of the most counterintuitive aspects of the process, and it is central to understanding why black holes appear so mysterious from the outside. Collapse does not unfold the same way for all observers. Instead, the experience of time itself depends on where the observer is located and how strongly space-time is curved by gravity. This is not a philosophical idea, but a physical reality predicted by general relativity and confirmed by experiment in weaker gravitational fields. For an observer far from the collapsing star, the approach to black hole formation appears to slow dramatically as the core contracts. As matter falls inward, a light emitted from it must climb out of an increasingly deep gravitational well. In doing so, that light loses energy and becomes red-shifted, stretched to longer wavelengths. Signals take longer to arrive. Each pulse of light arrives later and weaker than the last. To the distant observer, the collapsing star never quite finishes collapsing. It fades, slows, and disappears, frozen in time at the threshold of the event horizon. This apparent freezing is not because collapse halts. It is because time near the forming black hole flows more slowly relative to time far away. Clocks close to the collapsing core tick at a slower rate. As the event horizon forms, this time dilation becomes extreme. From far away, the formation of the horizon appears to take an infinite amount of time. From nearby, it takes only moments. For the matter falling inward, the experience is entirely different. Locally, nothing unusual happens at the event horizon. The laws of physics remain unchanged. Forces behave normally. Clocks tick steadily. The infalling matter crosses the horizon in a finite amount of proper time. It does not experience an infinite delay or a sudden stop. The horizon is not a physical surface. It is a boundary defined by the structure of space-time, not by matter or force. This difference in experience creates a profound divide between perspectives. From the outside, the black hole never quite finishes forming. From the inside, it forms completely and immediately. Both descriptions are correct. They reflect the fact that time is not absolute. It is shaped by gravity. Inside the event horizon, the nature of time changes even more radically. In ordinary space, one can choose to move forward, backward, or sideways. Inside a black hole, this freedom vanishes in one direction. The inward direction becomes unavoidable, like the passage of time itself. Just as one cannot choose to stop time from advancing, one cannot choose to stop moving inward once the horizon is crossed. This is not due to force or acceleration. It is due to the geometry of space-time. This geometric inevitability defines the interior of a black hole. The center is not simply a place. It is a future. All possible paths lead toward it. This is why escape is impossible. It is not because gravity pulls too hard, but because the structure of space-time no longer allows outward trajectories. The concept of simultaneity also breaks down during collapse. Events that appear simultaneous to one observer are not simultaneous to another. The formation of the horizon, the collapse of the core, and the emission of signals cannot be ordered in a single universal sequence. Different observers construct different timelines, each consistent within their own frame of reference. This breakdown challenges everyday intuition. Humans experience time as a shared, universal flow. Black hole birth reveals that this intuition is limited. Time is local. It depends on motion and gravity. Extreme collapse exposes this dependency in its most dramatic form. These time effects are not merely theoretical. They influence how black hole formation is observed. Astronomers never see matter cross an event horizon directly. Instead, they observe fading emission, gravitational waves, and indirect signatures. How the black hole announces itself not through a visible boundary, but through the absence of signals beyond a certain point. Gravitational waves offer a unique perspective on time during collapse. Unlike light, gravitational waves are distortions of space-time itself. They are less affected by intervening matter and carry information about the dynamics of collapse directly. In asymmetric collapse or binary formation, these waves encode the timing and motion of mass as it rearranges. They provide clues about processes occurring near the threshold of horizon formation. The timing of gravitational wave signals also reflects relativistic effects. Waveforms stretch and evolve in ways that depend on the masses and velocities involved. By analyzing these patterns, scientists can infer how quickly collapse occurred, how mass was distributed, and how space-time responded. The extreme time dilation near black hole formation also has implications for causality. Signals emitted just before horizon formation can reach distant observers, but signals emitted just after cannot. This creates a sharp causal boundary. Information from within the horizon is permanently disconnected from the outside universe. This separation is absolute within current physical understanding. This causal separation reinforces the idea that black hole birth is not a single moment that can be pinpointed universally. It is a process whose definition depends on perspective. From one frame, it is never complete. From another, it is inevitable and final. Understanding this duality is essential to grasping what a black hole truly is. It is not an object in the traditional sense. It is a region of space-time defined by causal structure. Its birth is the moment when that structure changes irreversibly. This irreversibility gives black holes a unique status in physics. Most processes can, in principle, be reversed. black hole formation cannot. Once the horizon forms, no known mechanism can restore the original star or reveal its interior. The universe has crossed a boundary that cannot be undone. This finality connects black hole birth to fundamental questions about time itself. Why does time have a direction? Why do some processes move inexorably forward? Black holes embody these questions physically. Their formation marks a point beyond which reversal is impossible. When quantum physics enters the discussion of black hole birth, certainty gives way to open questions. General relativity describes collapse with extraordinary accuracy up to the event horizon. Yet it remains silent about what ultimately happens at the smallest scales. Quantum mechanics governs matter at those scales, but it does not yet incorporate gravity in a complete way. The birth of a black hole sits precisely at the intersection of these two frameworks, exposing the limits of both. As collapse proceeds and density rises, matter is forced into regimes far beyond those encountered elsewhere in the universe. Atomic structure dissolves. Nuclei overlap. The distinction between particles becomes blurred. In this extreme environment, quantum effects that are normally negligible become significant. Yet gravity continues to dominate. The question is not whether quantum mechanics applies, but how it modifies the outcome predicted by classical gravity. One of the central issues is the fate of information. In classical descriptions, once matter passes inside the event horizon, all information about its internal state is lost to the outside universe. The black hole is fully characterized by mass, spin, and charge. This simplicity is known as the no-hair property. Quantum mechanics, however, insists that information cannot be destroyed. Every physical process must preserve information in some form. This tension becomes unavoidable at black hole birth. If information truly disappears behind the horizon, quantum theory is violated. If it is preserved, it must be encoded in a way not described by classical spacetime geometry. Resolving this contradiction has driven decades of research and remains one of the most important open problems in theoretical physics. Some proposals suggest that information is stored at or near the event horizon, subtly encoded in quantum correlations. Others propose that spacetime itself must be modified at very small scales, preventing the formation of a true singularity. In these models, collapse may reach an extremely dense but finite state rather than an infinite one. While these ideas are mathematically sophisticated, none have yet been confirmed experimentally. What is clear is that black hole birth challenges the notion that space-time is continuous at all scales. Near the center of collapse, distances become so small that classical concepts of geometry may lose meaning. Quantum fluctuations of space-time itself may become important. At this point, the familiar idea of a smooth fabric gives way to something more granular, though its precise nature remains unknown. Despite these uncertainties, the external behavior of black holes is remarkably well understood. Observations of black hole mergers through gravitational waves match predictions from general relativity with astonishing precision. This indicates that whatever quantum effects occur near the center do not significantly alter the large-scale structure of spacetime outside the horizon. The classical description remains valid where it can be tested. This separation of scales allows scientists to study black hole birth with confidence in many respects, even while acknowledging ignorance at the deepest level. The formation of the horizon, the emission of gravitational waves, and the interaction with surrounding matter are all described accurately by existing theory. The unresolved questions lie beyond observational reach, hidden behind causal boundaries. The possibility that black holes evaporate over extremely long timescales introduces another layer of complexity. According to quantum field theory in curved spacetime, black holes are not entirely black. They emit radiation due to quantum effects near the horizon, a process that would eventually cause them to lose mass and disappear. This radiation is extraordinarily weak for stellar mass and larger black holes, making it irrelevant for their formation and early evolution. But it raises profound questions about the ultimate fate of information. If black holes evaporate completely, much information must somehow be released back into the universe. How this occurs and how it relates to the original collapse remains unclear. These questions tie the birth and death of black holes into a single, unresolved narrative, connecting the beginning and end of these objects through quantum principles. From an observational standpoint, black hole birth is studied through indirect evidence. Supernova remnants, gravitational wave signals, and the motion of nearby objects all provide clues. Each observation adds constraints, narrowing the range of possible models. As detectors become more sensitive, these constraints improve, sharpening understanding of how black holes form in different environments. The study of black hole formation also informs understanding of extreme states of matter. Neutron stars represent one such state, each supported by quantum pressure. Black holes represent the point where that support fails. Understanding where this transition occurs constrains theories of dense matter, including how particles behave at densities beyond those achievable in laboratories. This connection has practical implications for interpreting astrophysical data. Measurements of neutron star masses and radii, for example, help determine the maximum mass such objects can support. Observations of black hole masses indicate where collapse must have continued. Together, these observations bracket the unknown physics of ultra-dense matter. Black hole birth also plays a role in shaping cosmic environments. The energy released during collapse and subsequent accretion influences surrounding gas and star formation. In galaxies, growing black holes can regulate the formation of new stars by heating or expelling gas. This feedback links the smallest scales of collapse to the largest scales of structure formation. The universality of black hole formation underscores a deeper principle. Gravity does not care about composition. Whether matter is hydrogen, iron, or exotic particles, gravity responds only to energy and mass. When concentration exceeds a threshold, collapse proceeds. This universality makes black holes powerful probes of fundamental physics. At the same time, the mystery at their core reminds us that current theories are incomplete. Black holes are not failures of understanding. They are signposts. They mark where known laws succeed brilliantly and where they must be extended. Confirming that a black hole has been born is not a matter of direct observation. By definition, the event horizon prevents light or information from escaping once it forms. Instead, astronomers rely on indirect evidence, assembling a consistent picture from multiple observations that together leave no alternative explanation. Black hole birth is inferred through absence as much as presence, through what suddenly stops as much as what appears. One of the earliest indicators comes from stellar collapse events, where the expected aftermath fails to appear. In some massive star deaths, a bright supernova explosion is observed, followed by a compact remnant whose properties can be measured. In others, the star simply vanishes. Observations have revealed massive stars that abruptly dim and disappear without producing a strong supernova. The most plausible explanation is that the star collapsed directly into a black hole, with little energy released to expel its outer layers. These failed supernovae provide strong evidence for direct collapse black hole formation. Another powerful method involves tracking the motion of objects influenced by an unseen mass. In binary systems, a visible star may orbit an invisible companion. By measuring the star's motion, astronomers can calculate the mass of the unseen object. If that mass exceeds the maximum possible mass of a neutron star, the conclusion is unavoidable. A black hole must be present. In these systems, the black hole's birth is inferred from its gravitational influence long after collapse has occurred. Accretion provides additional evidence. When gas falls toward a compact object, it heats up and emits radiation. The pattern of this radiation depends on the nature of the object. Neutron stars have solid surfaces that produce characteristic signals when infalling matter strikes them. Black holes lack such surfaces. Matter disappears silently across the horizon. This difference produces distinct observational signatures in X-ray emission, allowing astronomers to distinguish between neutron stars and black holes. The most definitive evidence of black hole formation comes from gravitational waves. When massive objects move asymmetrically or merge, they generate ripples in spacetime that carry information about their masses, spins, and dynamics. Gravitational wave detectors have observed signals that can only be explained by black hole mergers. These observations confirm not only that black holes exist, but that they form through collapse and subsequent interactions, exactly as predicted by theory. Some gravitational wave events appear to involve black holes forming directly from collapsing stars or merging with neutron stars. The waveforms encode the moment when a horizon must have formed. These detections offer a new way to study black hole birth, independent of electromagnetic radiation. They reveal processes that would otherwise remain hidden. Timing also plays a critical role in identifying black hole formation. In core collapse supernovae, neutrinos are emitted in vast numbers. These neutrinos escape before light, carrying information from deep within the star. A sudden cutoff in neutrino emission may signal the formation of an event horizon, marking the moment when even neutrinos can no longer escape. Detecting such a cutoff would provide a direct timestamp for black hole birth, though such observations remain rare. The combination of electromagnetic signals, neutrinos, and gravitational waves represents a multi-messenger approach to studying collapse. Each messenger provides different information. Light reveals what happens in the outer layers. Neutrinos probe the core. Gravitational waves trace the motion of mass and spacetime. Together, they allow reconstruction of events that no single signal could describe alone. These methods also help distinguish black hole formation from other outcomes. Neutron stars produce pulsations, magnetic activity, and surface emission. Black holes do not. The absence of these features, combined with mass measurements, strengthens identification. Over time, patterns emerge that clarify which stars produce black holes and under what conditions. Observational evidence has also revealed diversity in black hole birth. Some black holes receive strong kicks at birth, launched through space by asymmetries and collapse. Others remain near their birthplaces. These differences reflect variations in collapse dynamics, rotation, and explosion asymmetry. Studying these motions helps refine models of stellar death. Population studies further constrain formation pathways. By measuring the masses and spins of large numbers of black holes, scientists can infer how they formed. Rapidly spinning black holes may have inherited rotation from their progenitor stars or gained it through accretion. Slowly spinning ones may have formed through direct collapse with little angular momentum. These patterns reveal the histories encoded in black hole properties. The environment also leaves its mark. Black holes formed in dense clusters may undergo repeated interactions and mergers, altering their masses and spins. Those formed in isolation evolve differently. Comparing these populations helps disentangle formation channels. Despite this growing body of evidence, black hole birth remains challenging to observe in real time. The most direct signals are fleeting, faint, or obscured. Progress depends on patience, improved detectors, and global coordination. Each new observation adds a piece to the puzzle. What emerges from this effort is a coherent picture. Black holes are not hypothetical constructs. They are inevitable outcomes of gravity acting on sufficient mass, and their birth is a natural consequence of known physics pushed to its limits. Observations across multiple channels confirm this conclusion repeatedly. At the same time, each confirmed black hole deepens the mystery of what lies beyond the horizon. Birth marks a boundary not only in space-time, but in knowledge. Beyond that boundary, questions remain unanswered. Once a black hole is born, its influence extends far beyond the moment of collapse. Although the formation itself may be brief on cosmic timescales, the consequences unfold over millions and billions of years. Black holes become long-term architects of their environments, shaping the evolution of stars, gas, and entire galaxies. Their birth is not an endpoint, but the beginning of a prolonged interaction between extreme gravity and the surrounding universe. In stellar systems, newborn black holes often remain bound to companions. When a black hole forms in a binary system, the sudden loss of mass during collapse can alter the system's orbit. In some cases, the system is disrupted entirely, sending the black hole and its companion drifting apart. In others, the pair remains bound, entering a new phase of evolution dominated by accretion. Gas drawn from the companion star spirals inward, forming an accretion disk that radiates intensely. These systems become some of the brightest X-ray sources in the sky, revealing the presence of the otherwise invisible black hole. The rate at which a black hole grows depends on how efficiently it can capture matter. Accretion is not a simple process. Gas must lose angular momentum to fall inward, and this loss occurs through turbulence, magnetic interactions, and radiation. As gas heats up, radiation pressure can push outward, limiting how quickly matter can be consumed. This balance defines a natural upper limit to steady growth, shaping the evolution of black holes over time. In dense stellar environments, such as globular clusters, black holes interact dynamically with other stars and compact objects. These interactions can lead to the formation of binaries, exchanges of partners, and eventual mergers. Each merger increases the black hole's mass and alters its spin. Over time, these processes can produce black holes far more massive than those formed from single stellar collapses. This pathway may contribute to the population of intermediate mass black holes. On galactic scales, the influence of black holes becomes even more profound. Supermassive black holes at the centers of galaxies grow through a combination of accretion and mergers. As they consume gas, they release enormous amounts of energy in the form of radiation and jets. This energy interacts with the surrounding interstellar medium, heating it and sometimes expelling it from the galactic core. This feedback regulates star formation, preventing galaxies from converting all their gas into stars too quickly. This regulatory role suggests a deep connection between black hole growth and galaxy evolution. Observations show strong correlations between the mass of a galaxy's central black hole and properties of the galaxy itself, such as the mass of its central bulge. These correlations imply that black holes and galaxies grow together, influencing each other over cosmic time. The birth of a black hole thus has implications far beyond its immediate surroundings. The timing of black hole formation also matters. Black holes formed early in the universe had access to abundant gas and frequent mergers, allowing rapid growth. Those formed later often evolve more slowly, limited by reduced gas supply and fewer interactions. This difference helps explain why some black holes reached enormous masses so quickly, while others remained relatively small. Black hole birth also contributes to the production of gravitational waves over cosmic history. Binary systems formed from newborn black holes gradually lose energy through gravitational radiation, spiraling inward until they merge. These mergers produce signals that can be detected across vast distances, offering insight into populations of black holes formed long ago. Each detection is a delayed echo of earlier birth events. The cumulative effect of black hole formation and growth influences the large-scale structure of the universe. Energy injected by black holes affects the distribution of gas in galaxies and clusters, shaping cosmic environments. These effects must be accounted for in models of structure formation to accurately reproduce observed galaxy populations. Despite their influence, black holes remain elusive. Their birth leaves few direct traces, and their interiors are forever hidden. Yet their presence is unmistakable in the patterns they imprint on their surroundings. By studying these patterns, scientists infer the history of black hole formation across cosmic time. This indirect approach highlights the interconnectedness of cosmic processes. Black hole birth is linked to stellar evolution, galaxy assembly, and the behavior of matter under extreme conditions. Understanding it requires integrating observations across scales and epochs. The long-term stability of black holes also raises questions about the ultimate fate of the universe. While black holes persist for extraordinarily long times, they are not eternal. Over timescales vastly exceeding the current age of the universe, quantum processes may cause them to lose mass and eventually disappear. This distant future connects back to their birth, completing a life cycle that spans unimaginable durations. For now, black holes remain dominant actors in cosmic evolution. Their birth marks the formation of enduring structures that shape the universe long after the original stars have vanished. Each black hole carries within it a history of collapse, growth, and interaction, encoded in its mass and spin. The possibility that some black holes formed in the earliest moments of the universe adds an additional layer to the story of black hole birth. These hypothetical objects, known as primordial black holes, would not have originated from stars at all. Instead, they may have formed directly from density fluctuations in the hot, rapidly expanding universe shortly after the Big Bang. If certain regions contained slightly more mass than their surroundings, gravity could have caused those regions to collapse before pressure and expansion could disperse them. In the early universe, conditions were radically different from those that exist today. Matter and radiation were tightly coupled, temperatures were extreme, and small variations in density could have significant consequences. Unlike later epochs, there were no stars, no galaxies, and no heavy elements. Collapse during this time would have been governed almost entirely by the behavior of space-time and energy density itself. If primordial black holes formed, they would represent the earliest gravitational structures in the universe. The mass of a primordial black hole would depend on the size of the region that collapsed. Some could have been extremely small, far less massive than stars, while others could have rivaled stellar-mass black holes or more. This wide range of possible masses makes primordial black holes a subject of intense interest, as they could contribute to dark matter or influence cosmic evolution in subtle ways. However, their existence remains unconfirmed, and observational constraints limit how abundant they can be. Even if primordial black holes exist, their formation follows the same fundamental principle as all black holes. When mass or energy is compressed within a region small enough that gravity overwhelms all opposing forces, space-time collapses. The difference lies not in the mechanism, but in the environment. Black hole birth does not require stars. It requires only sufficient concentration of energy. Another extreme pathway to black hole formation involves direct collapse in the early universe, without passing through normal stellar stages. In some regions, massive clouds of gas may have avoided fragmenting into stars due to intense radiation fields or other effects that suppressed cooling. Without fragmentation, these clouds could collapse rapidly, or forming massive black holes directly. These objects may have served as seeds for the supermassive black holes observed at galactic centers today. These direct collapse black holes would have formed quietly, without the dramatic supernova explosions associated with stellar deaths. Their birth would have been marked primarily by the sudden appearance of a deep gravitational well, altering the motion of nearby gas and shaping subsequent structure formation. This pathway helps explain how extremely massive black holes could exist so early in cosmic history. The study of early black hole formation is closely tied to observations of distant galaxies and quasars. Quasars are powered by accretion onto supermassive black holes, and their brightness allows them to be observed across vast distances. Discovering quasars at high redshifts indicates that massive black holes were already in place when the universe was young. Understanding how these black holes formed challenges models of collapse and growth. Observations suggest that the first black holes formed rapidly, taking advantage of dense environments and abundant fuel. Their growth influenced the surrounding universe, contributing to the reionization of gas and shaping early galaxies. In this way, black hole birth played a role in transforming the universe from a uniform, opaque state into the structured cosmos observed today. The connection between early black holes and later cosmic evolution underscores the importance of collapse processes at different times. While stellar mass black holes dominate later epochs, early black holes may have set initial conditions that influenced everything that followed. Their gravitational pull helped gather matter, seeding the formation of galaxies and clusters. Studying these early pathways relies on indirect evidence. Gravitational waves may eventually reveal mergers involving early formed black holes, offering clues about their origins. Future detectors with greater sensitivity to low-frequency waves may detect signals from massive black hole mergers at high redshift, providing direct insight into early black hole populations. Theoretical models of early black hole formation also inform understanding of fundamental physics. They constrain inflationary scenarios, particle physics models, and the behavior of matter under extreme conditions. Black hole birth thus connects cosmology, astrophysics, and fundamental theory. Despite progress, many questions remain open. How common were primordial black holes, if they exist at all? What conditions allowed direct collapse black holes to form? How did early black holes interact with their environments? Each question reflects the complexity of the early universe and the challenge of reconstructing its history. What remains consistent across all these scenarios is the role of gravity as the decisive force. Whether in a dying star or the primordial universe, gravity shapes outcomes when other forces are unable to resist. Black hole birth is the ultimate expression of this dominance. As observations continue to improve, the picture of black hole formation across cosmic time will become clearer. Each new detection adds a constraint, narrowing possibilities and refining models. The story of black hole birth is not static. It evolves as evidence accumulates. Black hole birth confronts physics with absolute limits, forcing a reconsideration of how nature behaves when pushed to extremes. These limits are not arbitrary. They arise from the structure of physical laws themselves, revealing boundaries beyond which familiar concepts no longer apply. The formation of a black hole marks the point where matter, energy, and space-time reach configurations that cannot be described using ordinary intuition. One of the most important limits revealed by black hole formation is the maximum density matter can achieve before collapse becomes unavoidable. In stars, pressure generated by nuclear reactions and quantum effects counteracts gravity. White dwarfs rely on electron degeneracy pressure. The neutron stars rely on neutron degeneracy pressure and strong nuclear forces. Each stage represents a more compact and extreme state of matter. Black hole birth occurs when even these mechanisms fail, indicating a fundamental ceiling on how much resistance matter can provide. This ceiling is closely related to the concept of maximum mass for compact objects. Observations of neutron stars show that they cannot exceed a certain mass without collapsing further. This mass limit constrains theories of dense matter and the behavior of particles under extreme pressure. Black holes occupy the regime beyond this limit, where no stable configuration of matter is possible. The formation of an event horizon introduces another fundamental boundary. The horizon is not just a feature of black holes. It represents a causal limit in spacetime. Beyond this boundary, events cannot influence the outside universe. This separation enforces a strict division between observable and unobservable regions. Unlike other boundaries in physics, this one is absolute within current understanding. This causal boundary has profound implications for determinism and predictability. In classical physics, knowing the present state of a system allows prediction of its future. Black hole birth disrupts this ideal. Once information crosses the horizon, it cannot be accessed to inform future predictions. This loss challenges traditional notions of predictability and raises questions about whether physical laws remain complete descriptions of reality. Energy conditions also come into focus during collapse. General relativity assumes certain properties of matter and energy, such as positivity and stability. Black hole formation tests these assumptions at their limits. So far, observations support the idea that these conditions hold, allowing horizons to form as predicted. Any deviation could signal new physics, making black hole birth a critical testing ground. The concept of singularity further emphasizes these limits. Classical theory predicts that collapse leads to a point or region where density and curvature become infinite. At such extremes, equations lose meaning. Whether singularities truly exist or are replaced by new structures remains unknown. What is clear is that black hole birth pushes theories to their breaking point. Quantum gravity is expected to play a role in resolving these issues. A complete theory unifying quantum mechanics and gravity may replace singularities with finite, pseudo-extreme, states. Such a theory could alter the final stages of collapse without changing the external appearance of black holes. This possibility highlights how black hole birth bridges known and unknown physics. Despite these deep uncertainties, the external consistency of black hole behavior provides reassurance. Predictions about horizons, gravitational waves, and accretion match observations with remarkable accuracy. This suggests that any new physics operates at scales hidden from view, preserving the validity of existing models where they can be tested. Black hole birth also illuminates the relationship between geometry and energy. Gravity is not a force acting within space-time, but a manifestation of space-time curvature itself. Collapse demonstrates how energy shapes geometry dynamically, creating regions where geometry becomes dominant. This geometric perspective unifies diverse phenomena under a single framework. The study of black hole formation thus serves as a guide for extending physical theories. By identifying where existing models fail, it points toward what must be addressed. These failures are not random. They occur under specific, extreme conditions, providing valuable clues. This role extends beyond theoretical interest. Understanding limits on density, pressure, and energy informs models of astrophysical objects and cosmic evolution. It shapes expectations for what can exist and how the universe behaves under extreme conditions. Black holes also challenge assumptions about simplicity and complexity. They are among the simplest objects describable by physics, yet their formation involves some of the most complex processes known. This contrast underscores the richness of gravitational phenomena. As observations accumulate, constraints on extreme physics tighten. Gravitational wave measurements probe strong field gravity directly. Neutron star observations constrain dense matter equations of state. Together, they narrow the range of viable theories, guiding future work. The boundaries revealed by black hole birth are not endpoints. They are invitations to explore deeper layers of reality. Each limit encountered suggests that understanding can be extended, provided new frameworks are developed. The birth of a black hole forces a reconsideration of how observation itself works in the universe. In most physical situations, observation is assumed to be limited only by technology, and with better instruments, smaller scales, and greater distances can be explored. Black holes introduce a fundamentally different limitation. Their defining feature is not that they are difficult to observe, but that parts of them are permanently unobservable. This distinction reshapes the meaning of knowledge in physics. When a black hole forms, the event horizon establishes a boundary beyond which events cannot affect the outside universe. This boundary is not a matter of obscuration, like a cloud blocking light. It is a causal separation written into the structure of space-time. No improvement in instrumentation can overcome it. The interior is not hidden by distance or interference. It is disconnected. This disconnection has deep implications for how physical theories are constructed. Traditionally, our physics aims to describe systems completely, specifying initial conditions and predicting outcomes. Black hole birth challenges this goal by introducing regions whose internal states cannot be fully specified by external measurements. The exterior description remains precise, but it is incomplete with respect to the interior. This incompleteness does not mean black holes are poorly understood. On the contrary, their external properties are among the best tested predictions of general relativity. The challenge lies in reconciling this external precision with the internal inaccessibility. The question becomes not how to observe more, but how to define what it means to describe a physical system. Black hole birth also alters the role of the observer. In classical physics, observers are assumed to share a common description of events. Or, in relativistic contexts, this assumption breaks down. Observers following different paths through space-time experience different sequences of events. During collapse, one observer may never see a black hole fully form, while another experiences crossing the horizon in finite time. Both descriptions are valid within their respective frames. This multiplicity of perspectives does not imply contradiction. It reflects the relativity of simultaneity and the local nature of time. Black hole formation brings these abstract principles into sharp focus, transforming them from mathematical curiosities into physical realities with observable consequences. The distinction between inside and outside also raises questions about the nature of reality itself. If a region of space-time exists but cannot influence the rest of the universe, in what sense is it part of physical reality? Physics traditionally concerns itself with measurable quantities. Black hole interiors challenge this criterion, existing beyond measurement while still influencing external geometry. This tension has led to different interpretive approaches. Some emphasize operational definitions, focusing only on what can be measured. Others argue that reality extends beyond observation, and that interior regions must be included, even if inaccessible. Black hole birth forces this debate into concrete form. The causal structure created by black hole formation also influences ideas about determinism. In a deterministic universe, future states follow uniquely from present conditions. Event horizons complicate this picture by removing information from the observable domain. Whether this loss is fundamental or apparent remains an open question tied to quantum considerations. These issues are not confined to philosophy. They influence how physical laws are formulated. Any theory that claims completeness must account for regions that cannot be directly probed. Black holes provide a testing ground for such claims, revealing strengths and limitations. The study of black hole birth thus becomes a study of the relationship between law and observation. It highlights that physical laws are not merely descriptions of what happens, but frameworks that define what can be known. Horizons enforce boundaries on knowledge that no refinement can erase. This perspective also affects how predictions are evaluated. In many areas of science, predictions are validated by direct measurement. In black hole physics, validation often involves consistency rather than direct access. The agreement between different observations, theoretical predictions, and indirect measurements builds confidence in models that cannot be fully verified. Gravitational waves play a key role in this validation. They carry information from regions where gravity is strong but still observable. They allow tests of predictions near the threshold of horizon formation. Their agreement with theory strengthens confidence that the unseen interior behaves consistently with external laws. Black hole birth also influences broader interpretations of cosmology. If horizons exist on smaller scales, similar structures may exist on larger ones. Cosmic horizons, such as those associated with the universe's expansion, impose analogous limits on observation. Studying black holes informs understanding of these larger-scale boundaries. The presence of horizons emphasizes that the universe is not fully transparent to itself. There are limits to what any observer can know, imposed not by ignorance, but by structure. Black hole formation is a vivid demonstration of this principle. Yet within these limits, understanding continues to grow. By studying what black holes do to their surroundings, by measuring their mass, spin, and influence, scientists reconstruct aspects of their history. Black hole birth, though partially hidden, leaves traces that can be analyzed. These traces form a bridge between the observable and the unobservable. They allow inference without direct access, expanding knowledge while respecting fundamental boundaries. This balance between reach and restraint characterizes the study of extreme phenomena. Because black hole birth cannot be observed directly from start to finish, simulations play a central role in understanding how collapse unfolds. These simulations are not visualizations created for illustration. They are numerical experiments grounded in the equations of general relativity, nuclear physics, and fluid dynamics. By solving these equations step by step, scientists recreate the conditions inside collapsing stars and explore outcomes that cannot be reproduced in laboratories. Simulating black hole formation is extraordinarily challenging. The equations governing gravity are nonlinear, meaning small changes can produce large effects. As collapse proceeds, densities rise, timescales shrink, and space-time curvature becomes extreme. Numerical models must track matter moving at relativistic speeds, interacting through nuclear forces, emitting neutrinos, and reshaping space-time simultaneously. Each of these components requires careful approximation, and combining them pushes computational limits. Early simulations focused on simplified models, assuming symmetry and neglecting certain interactions. These models captured the basic picture of collapse, but missed important details. As computing power increased, simulations incorporated rotation, magnetic fields, and detailed neutrino transport. These additions revealed that black hole birth is not perfectly spherical or uniform. Small asymmetries can influence the outcome, affecting whether collapse halts temporarily or proceeds directly to a black hole. Rotation, in particular, plays a crucial role. Simulations show that rapidly rotating cores can flatten and develop complex internal flows. Magnetic fields can be amplified dramatically during collapse, influencing the dynamics of the surrounding material. In some cases, these effects drive jets that carry energy away from the core. While such processes do not prevent black hole formation when mass exceeds critical limits, they shape the observable signatures associated with collapse. Neutrino physics is another critical component. During collapse, vast numbers of neutrinos are produced and escape, carrying away energy and lepton number. Simulating neutrino transport accurately is essential for predicting whether a supernova explosion occurs or fails. Small differences in neutrino interactions can determine whether the outer layers of a star are expelled or fall back into the forming black hole. These simulations also help define the boundary between neutron star and black hole outcomes. By varying parameters such as core mass, rotation rate, and equation of state for dense matter, scientists identify the conditions under which neutron degeneracy pressure can temporarily halt collapse. When these conditions are not met, simulations show collapse proceeding inexorably toward horizon formation. Importantly, simulations reveal that black hole birth is not always a clean, instantaneous transition. In some cases, a neutron star forms briefly before collapsing further as additional mass falls back. This delayed collapse produces distinct signatures, including extended neutrino emission followed by abrupt cutoff. Such scenarios offer potential observational markers for black hole formation. Numerical models also explore direct collapse scenarios relevant to early cosmic history. Simulations of massive gas clouds show how cooling, radiation, and angular momentum influence whether fragmentation occurs. When fragmentation is suppressed, collapse can proceed rapidly, forming massive black hole seeds. These results support pathways for early supermassive black hole formation. The reliability of simulations depends on validation against observations. Gravitational wave detections provide key tests. The waveforms observed from black hole mergers match predictions from numerical relativity with remarkable accuracy. This agreement builds confidence that simulations capture essential physics, even when direct observation is impossible. Simulations also guide interpretation of electromagnetic signals. By modeling accretion flows and jet formation, scientists connect observed radiation patterns to underlying dynamics. This connection allows inference about black hole birth environments and subsequent evolution. Despite their power, simulations are not definitive. They rely on assumptions about unknown physics, particularly at extreme densities. Different choices for equations of state or neutrino interactions can lead to different outcomes. Comparing results across models helps identify robust features and isolate uncertainties. This iterative process reflects how knowledge advances in extreme regimes. Theory suggests possibilities. Simulations explore consequences. Observations constrain models. Together, they converge toward understanding, even when direct access is denied. The development of simulation techniques also influences future discovery. Improved models inform detector design, helping identify which signals are most informative. They guide observational strategies, focusing attention on key signatures. In this way, simulations become part of the observational apparatus, extending perception into regimes beyond direct reach. They allow exploration of scenarios that cannot be witnessed but must be understood to interpret what is seen. As computational power continues to grow, simulations will become more detailed and realistic. They will incorporate more physics, higher resolution, and longer timescales. This progress promises deeper insight into the moment of black hole birth and the processes surrounding it. Black hole birth represents one possible endpoint in the life cycle of stars, but it is not the only one. To understand why some stars become black holes while others do not, it is necessary to place collapse within the broader context of stellar evolution. Stars are not born equal, and their final fates are determined largely at the moment of their formation by mass, composition, and environment. These initial conditions quietly dictate outcomes millions or billions of years later. Every star begins as a cloud of gas collapsing under gravity. As the cloud contracts, temperature and pressure rise until nuclear fusion ignites. From that moment onward, a star exists in a delicate balance between gravity and energy production. The duration and nature of this balance depend on mass. Low-mass stars burn fuel slowly and steadily, remaining stable for billions of years. Massive stars burn intensely and briefly, racing through their fuel and toward collapse. When low-mass stars exhaust their nuclear fuel, gravity causes them to contract, but not catastrophically. Electron degeneracy pressure halts collapse, leaving behind a white dwarf. These remnants cool gradually over time, fading quietly into darkness. There is no explosion, no violent transformation of spacetime, no horizon. Matter remains arranged in a stable configuration, supported by quantum effects. Stars with intermediate mass follow a more dramatic path. After exhausting fuel, their cores collapse rapidly, triggering supernova explosions. The collapse halts when neutron degeneracy pressure becomes dominant, producing neutron stars. These objects are extraordinarily dense, composed almost entirely of neutrons, yet they remain stable under specific conditions. Their existence marks a balance point between collapse and resistance. Black hole birth occurs when this balance fails. When the mass of the collapsing core exceeds the maximum supported by neutron degeneracy pressure, no stable configuration remains. The distinction between neutron star and black hole is therefore not qualitative, but quantitative. It is determined by mass crossing a threshold set by fundamental physics. This threshold is influenced by the equation of state of dense matter, which describes how pressure responds to density at extreme conditions. Different models predict slightly different maximum masses for neutron stars. Observations of massive neutron stars place constraints on these models, narrowing the range of possibilities. And when black hole masses are measured just above these limits, they provide complementary information. The transition from neutron star to black hole is one of the sharpest transitions in astrophysics. Below the threshold, matter organizes into an exotic but stable state. Above it, collapse becomes inevitable. There is no gradual intermediate object. This sharpness reflects the underlying physical limits governing matter. The environment in which a star evolves also affects its fate. Stars in binary systems can exchange mass, altering their evolution. A star that would have ended as a neutron star in isolation may become massive enough to form a black hole through accretion. Conversely, mass lost to a companion can prevent black hole formation. Binary interactions add complexity to predictions. Metallicity, then the abundance of elements heavier than hydrogen and helium, influences stellar winds and mass loss. High metallicity stars lose more mass, reducing their final core mass, Low metallicity stars retain more mass, increasing the likelihood of black hole formation. This dependence explains why black hole populations vary across cosmic history and environment. Stellar rotation also matters. Rapid rotation can alter internal mixing, extend nuclear burning phases, and influence collapse dynamics. While rotation alone cannot prevent black hole formation when mass is sufficient, it shapes the path to collapse and the properties of the resulting black hole. The comparison between different stellar endpoints highlights that black hole birth is not an anomaly. It is a natural extension of the same processes governing all stellar evolution. Stars are engines converting mass into energy until they reach limits set by physics. Black holes represent what happens when those limits are exceeded. This perspective demystifies black holes without diminishing their significance. They are not exotic intrusions into the universe, but outcomes consistent with known laws applied under extreme conditions. Their birth follows logically from principles governing stars of all masses. Understanding black hole formation also clarifies why such objects are rare compared to stars. Only a small fraction of stars are massive enough to produce black holes. Even among those, not all collapse directly. Many lose enough mass to avoid crossing critical thresholds. Black hole birth requires specific conditions, making it uncommon but inevitable in a universe with massive stars. The connection between stellar evolution and black hole formation underscores the continuity of cosmic processes. The same gravity that gathers gas into stars eventually pulls those stars apart. The same nuclear reactions that power starlight eventually cease, allowing gravity to dominate. Black hole birth is the final expression of this cycle. This cycle has consequences beyond individual stars. The distribution of stellar endpoints influences chemical enrichment, energy injection, and gravitational dynamics in galaxies. Supernovae spread heavy elements. Neutron stars produce magnetic fields and radiation. Black holes shape environments through gravity and accretion. Each endpoint contributes differently to cosmic evolution. By placing black hole birth within this broader context, its role becomes clearer, and it is not simply about collapse, but about balance and limits. It reveals how nature manages extremes, allowing stability when possible and collapse when necessary. The birth of a black hole leaves a permanent imprint on the surrounding spacetime, one that differs fundamentally from the gravitational influence of any other object. While all mass curves spacetime, the degree and structure of curvature near a newly formed black hole reach extremes unmatched elsewhere. This curvature governs how matter moves, how light travels, and how time flows in the region surrounding the collapse. Understanding this geometry is essential to grasping what makes black holes unique. Near ordinary stars, or even neutron stars, space-time curvature remains moderate. Objects can orbit stably, light paths bend gently, and tidal forces, while strong near-neutron stars remain finite and survivable under certain conditions. When a black hole forms, the curvature increases dramatically as one approaches the event horizon. Distances in the radial direction stretch, while circumferential paths compress in a way that defies everyday intuition. Tidal forces near a black hole depend strongly on its mass. For stellar mass black holes, these forces become extreme well outside the event horizon. Objects approaching such a black hole experience intense stretching in one direction and compression in another, a result of differential gravitational pull across their length. This effect, sometimes called tidal stretching, arises because gravity increases rapidly with decreasing distance. These forces grow stronger as collapse proceeds and the horizon forms. For more massive black holes, particularly supermassive ones, the situation is different. Their event horizons are much larger, and the gradient of gravity at the horizon is comparatively gentle. In these cases, tidal forces at the horizon may be relatively weak, allowing objects to cross without immediate disruption. This counterintuitive result reflects how mass and scale influence spacetime curvature. The geometry surrounding a black hole is described by precise solutions to Einstein's equations. These solutions reveal that once the horizon forms, spacetime becomes strongly asymmetric. The inward direction acquires a special status, with all possible paths leading toward the center. Outside the horizon, this asymmetry manifests as extreme curvature that governs motion. Light behaves in particularly striking ways near a newly formed black hole. Paths that would normally escape instead curve inward, looping around the black hole or falling across the horizon. There exists a region where light can orbit temporarily, trapped in unstable paths. These features are direct consequences of how space-time is shaped by collapse. The formation of the horizon also alters causal relationships. Events near the horizon influence the outside universe only up to a point. Beyond that, causal contact is severed. This reorganization of causality is not gradual. It occurs sharply when the horizon forms, marking a qualitative change in space-time structure. Time dilation near a black hole is another manifestation of curvature. Clocks closer to the horizon run increasingly slowly relative to distant observers. This effect grows stronger as collapse progresses. After formation, this time dilation becomes a permanent feature of the black hole's environment. It is measurable through the behavior of orbiting matter and the frequency shifts of emitted radiation. The curvature surrounding a black hole also affects stability of orbits. Unlike around stars, stable circular orbits exist only beyond a certain distance from the horizon. Inside this radius, known as the innermost stable orbit, matter cannot remain in steady motion. It must spiral inward. This property shapes accretion disks and influences how black holes interact with their surroundings. The birth of a black hole therefore creates a region where geometry, rather than force, dominates dynamics. Objects move not because they are pulled, but because space-time itself directs their paths. This geometric perspective distinguishes black holes from all other astrophysical objects. These geometric effects persist indefinitely. Once formed, the curvature pattern remains as long as the black hole exists. It changes only if the black hole gains or loses mass or angular momentum. In this sense, black hole birth establishes a long-lived structure in space-time. Studying this structure provides insight into gravity under extreme conditions. Observations of accretion flows, gravitational lensing, and gravitational waves probe the curvature near black holes, testing predictions of general relativity. So far, these predictions have been confirmed with remarkable accuracy, reinforcing confidence in the theory while highlighting areas for further exploration. The contrast between neutron stars and black holes is particularly instructive. Neutron stars possess surfaces and solid interiors that influence their gravitational fields. Black holes lack such features. Their curvature is entirely determined by mass and spin, making them simpler yet more extreme. This simplicity allows precise testing of gravitational theory. The formation of a black hole thus represents a transition from matter-dominated structure to geometry-dominated structure. Matter collapses to the point where it no longer determines the external configuration. Space-time takes over, imposing its own order. This transition has implications beyond astrophysics. It informs understanding of how geometry and matter interact at fundamental levels. and it raises questions about whether space-time itself has degrees of freedom that become relevant at extreme curvature. Rotation fundamentally changes how a black hole interacts with its surroundings, and this influence begins at birth. Very few stars are perfectly still. As a massive star collapses, its rotation rate increases dramatically due to conservation of angular momentum. Even a modest initial spin becomes extreme as the core contracts. When a black hole forms from this rotating collapse, it inherits that angular momentum, imprinting rotation into the surrounding spacetime itself. A rotating black hole does not simply curve spacetime inward. It drags spacetime around with it. This effect, known as frame dragging, means that the fabric of space is compelled to rotate in the direction of the black hole's spin. Though near the event horizon, this dragging becomes so strong that no object can remain stationary relative to distant space. Everything is carried along, regardless of its own motion. The presence of rotation creates a region outside the event horizon where energy behaves in unfamiliar ways. In this region, space-time is dragged faster than objects can resist. Motion against the direction of rotation becomes impossible. This creates conditions under which energy can be extracted from the black hole's rotation, reducing its spin while transferring energy outward. This process does not violate conservation laws. It relies on the fact that the black hole's rotational energy is stored in space-time geometry itself. Energy extraction mechanisms become particularly important for newborn black holes surrounded by dense material. Magnetic fields anchored in surrounding plasma can tap into rotational energy, launching powerful jets along the black hole's rotational axis. These jets can extend vast distances, transporting energy far from the site of collapse. While the black hole itself emits nothing, its rotation enables surrounding matter to become one of the most luminous phenomena in the universe. The efficiency of these processes depends on spin. Rapidly rotating black holes can release more energy through accretion and jet formation than slowly rotating ones. This connection allows astronomers to infer spin indirectly by observing emissions from accreting systems. These observations provide clues about how black holes formed and how much angular momentum they inherited at birth. The role of rotation also influences the stability of accretion disks. Around rotating black holes, the innermost stable orbit moves closer to the event horizon. Matter can orbit deeper in the gravitational well before plunging inward, increasing the energy released through radiation. This effect enhances the brightness of accreting black holes and shapes their observable signatures. Rotation further complicates the geometry of spacetime. The horizon itself is distorted, becoming oblate rather than spherical. Paths of particles and light are twisted, producing complex motion patterns. These effects must be accounted for when interpreting observations, especially in regions close to the horizon. The birth of a rotating black hole also affects gravitational wave emission. In asymmetric collapse or in binary systems, rotation alters the waveforms produced. The frequency, amplitude, and evolution of these waves encode information about spin and mass. Observations of gravitational waves thus provide a direct probe of black hole rotation at formation. Spin evolution continues after birth. Accretion can spin black holes up or down, depending on the orientation of incoming matter. Mergers with other black holes can dramatically alter spin, producing remnants with new rotational properties. However, the initial spin established at birth sets the stage for subsequent evolution. The interaction between rotation and environment has consequences on galactic scales. Jets powered by rotating supermassive black holes can regulate star formation, heat surrounding gas, and influence galaxy morphology. These effects trace back to the initial conditions of black hole formation and growth. Understanding rotation also clarifies why black holes can be so efficient at converting mass into energy. In some cases, a significant fraction of infalling matter's rest mass energy is radiated away before crossing the horizon. This efficiency surpasses that of nuclear fusion, making accreting black holes some of the most powerful engines known. Despite these dramatic effects, rotation does not alter the fundamental nature of black hole birth. The event horizon still forms when escape becomes impossible. The interior remains causally disconnected. Rotation enriches the external structure without changing the defining feature. This balance between simplicity and complexity is characteristic of black holes. They are defined by a small set of parameters, yet they produce a wide range of observable phenomena through interaction with their surroundings. Birth establishes these parameters, shaping future behavior. The study of rotation underscores the importance of angular momentum in cosmic evolution. From planets to galaxies, rotation influences structure and dynamics. Black hole birth represents the extreme end of this spectrum, where rotation shapes spacetime itself. Gravitational waves provide one of the most direct and unambiguous windows into black hole birth, particularly when collapse or formation occurs asymmetrically or in the presence of rotation. Unlike light, which can be absorbed, scattered, or blocked by matter, gravitational waves propagate through space-time itself. They carry information about motion and mass distribution without being significantly altered by the environments they pass through. This makes them uniquely suited for probing the most extreme stages of collapse. During the birth of a black hole, gravitational waves are produced when mass moves in a non-spherical way. Perfectly symmetric collapse would generate no gravitational radiation. But real stars are never perfectly symmetric. Rotation, turbulence, magnetic fields, and instabilities introduce asymmetry. As the core collapses, these asymmetries cause spacetime to oscillate, producing waves that travel outward at the speed of light. The character of these waves depends on how the black hole forms. In cases where a massive star collapses directly into a black hole without a strong supernova explosion, the gravitational wave signal is brief and subtle. It reflects the rapid contraction of the core and the sudden formation of the event horizon. In scenarios where a proto-neutron star forms temporarily before collapsing further, the signal is more complex. It may include oscillations associated with the neutron star phase, followed by a sharp change when the horizon forms. Rotation enhances gravitational wave emission. A rapidly spinning collapsing core produces stronger and more structured signals. The frequency and amplitude of these waves encode information about the mass, rotation rate, and internal dynamics of the collapsing object. By analyzing these waveforms, scientists can infer properties of black holes at birth that would otherwise remain hidden. Binary systems provide an even clearer gravitational wave signature, one when two massive stars evolve together and both collapse into black holes. They may form a black hole binary. As these black holes orbit each other, they emit gravitational waves continuously, losing energy and spiraling inward. The final merger produces a powerful burst of gravitational radiation that reveals the masses and spins of the black holes involved. These signals confirm not only that black holes exist, but that they form through collapse consistent with theoretical predictions. The detection of gravitational waves from black hole mergers has revolutionized understanding of black hole populations. Observations reveal black holes with masses larger than previously expected, suggesting formation in low metallicity environments or through direct collapse pathways. And the spins measured in these events provide clues about whether black holes formed in isolation or through repeated interactions in dense environments. Gravitational wave astronomy also allows tests of strong field gravity near black hole formation. The late stages of merger and collapse involve space-time curvature at its most extreme. The agreement between observed waveforms and predictions from general relativity confirms that the theory remains valid in regimes far beyond those previously tested. Any deviation would signal new physics. The timing of gravitational wave signals can also constrain formation scenarios. In core collapse events, waves may precede or accompany electromagnetic signals. Comparing arrival times helps reconstruct the sequence of events during collapse. In the future, coordinated observations across multiple messengers may capture black hole birth in unprecedented detail. As detectors become more sensitive, they may detect gravitational waves directly from collapsing stars that form black holes. Such detections would provide real-time confirmation of black hole birth, marking the moment when a horizon forms. Although these signals are expected to be faint and rare, their discovery would represent a major milestone. Gravitational waves also preserve information about early black hole formation across cosmic time. Waves from distant mergers carry signals generated billions of years ago, offering insight into the conditions under which those black holes formed. This allows reconstruction of black hole birth history on a universal scale. The study of these waves highlights the role of motion in shaping space-time. Black hole birth is not only about collapse, but about dynamic reconfiguration. Gravitational waves are the universe's record of that reconfiguration, written into geometry rather than matter. This perspective reinforces the idea that black holes are not isolated objects, but participants in a dynamic cosmos. Their formation sends ripples that propagate far beyond their immediate surroundings, connecting distant regions of space-time through shared history. As we continue, we will turn toward the final implications of black hole birth. We will examine what these processes reveal about the universe as a whole, how black holes influence cosmic structure over the longest timescales, and how their formation fits into the ultimate evolution of the cosmos. Black hole birth does not only mark the end of a star or the beginning of a compact object. It represents a turning point in the long-term evolution of the universe itself. Once formed, black holes persist for timescales that dwarf those of stars, planets, and even galaxies. Their longevity gives them a unique role in shaping cosmic history across billions and trillions of years. In the present universe, black holes act as anchors of structure. Stellar mass black holes populate galaxies quietly, influencing their immediate surroundings through gravity. Supermassive black holes dominate galactic centers, binding stars into coherent orbits and regulating the flow of gas. Their formation, often early in a galaxy's life, sets the stage for how that galaxy evolves. Over cosmic time, galaxies merge. When this happens, their central black holes are drawn together by gravitational interactions. Eventually, these black holes form binaries and merge, creating larger black holes. This hierarchical growth mirrors the growth of galaxies themselves. In this way, black hole birth and merger are woven into the fabric of large-scale cosmic structure. The energy released during black hole growth has lasting effects. Accretion-driven radiation and jets heat surrounding gas, preventing it from cooling and forming new stars too quickly. This feedback mechanism helps explain why galaxies do not grow indefinitely and why their observed properties fall within narrow ranges. Black hole birth thus contributes indirectly to shaping the visible universe. On even longer timescales, the influence of black holes becomes more pronounced as other sources of energy fade. Stars exhaust their fuel and die. Galaxies gradually lose their gas. In such a universe, black holes remain among the few active players. Their gravity continues to organize matter long after starlight has dimmed. The persistence of black holes also raises questions about the ultimate fate of matter. material that falls into black holes is removed from the observable universe, altering the distribution of mass over time. As black holes merge and grow, matter becomes increasingly concentrated. This concentration influences the universe's entropy, a measure of disorder that plays a central role in thermodynamics and cosmology. Black hole birth is closely tied to entropy increase. The formation of an event horizon corresponds to a dramatic increase in entropy, reflecting the number of internal states hidden from observation. This connection links black hole physics to fundamental laws governing time and irreversibility. The growth of black holes contributes to the overall arrow of time in the universe. In the far future, when conventional astrophysical processes have ceased, black holes may dominate the cosmic landscape. Their eventual evaporation through quantum processes would occur over timescales unimaginably longer than the current age of the universe. This distant future connects back to their birth, framing black holes as objects with life cycles that span cosmic eras. The existence of black holes also influences philosophical interpretations of the universe's end state, whether the universe expands forever, collapses, or approaches a steady state. Black holes play a role in shaping outcomes. Their birth marks the creation of regions of space-time that evolve largely independently from the rest of the universe. Understanding black hole formation therefore informs not only astrophysics, but cosmology. It shapes models of how structure forms, evolves, and eventually dissolves. Each black hole born adds a permanent feature to space-time, altering the universe's trajectory. These considerations highlight that black hole birth is not merely a local event. It has consequences that ripple outward across space and time. The collapse of a single star contributes, in a small but meaningful way, to the evolution of the cosmos as a whole. As observations continue and theories evolve, the role of black holes in cosmic history becomes clearer. Their formation marks moments when gravity asserts its dominance most completely, and these moments accumulate, shaping the universe's structure and fate. When all aspects of black hole birth are considered together, a coherent picture begins to emerge, one that reveals deep truths about gravity, matter, and space-time. The formation of a black hole is not an anomaly or breakdown of natural order. It is the most complete expression of gravity operating within the rules of the universe. Where other forces weaken, gravity persists, shaping outcomes with quiet inevitability. Gravity differs from other fundamental interactions in a crucial way. It cannot be screened or neutralized. Electric charges can cancel. Nuclear forces act only at short range. Gravity accumulates. Every particle with mass contributes. Black hole birth demonstrates the ultimate consequence of this accumulation. Then, when mass becomes sufficiently concentrated, gravity reshapes space-time so completely that escape is no longer a meaningful concept. This reshaping reveals that space-time is not a passive arena in which events unfold. It is an active participant, responding dynamically to energy and motion. During collapse, space-time bends, stretches, and reorganizes itself. The event horizon marks a transition in this structure, separating regions with fundamentally different causal relationships. This separation is not imposed from outside. It arises naturally from the equations governing gravity. The simplicity of black holes after formation stands in contrast to the complexity of the processes that create them. This contrast highlights a recurring theme in physics. Complex behavior can lead to simple outcomes governed by universal principles. The details of collapse fade, leaving behind an object described by a small set of parameters. This universality suggests that black holes capture something essential about gravity itself. The study of black hole birth also reinforces the idea that physical laws are context-dependent. Under everyday conditions, gravity appears weak and easily countered. Under extreme conditions, it dominates completely. The same equations apply in both cases, but their consequences differ dramatically. Black holes reveal the full range of gravity's influence. Matter, too, is revealed to have limits. Quantum effects provide remarkable resistance to compression, yet they are not absolute. There exists a threshold beyond which matter cannot maintain structure. Black hole birth marks the crossing of that threshold, and it shows where descriptions based on particles and forces give way to descriptions based on geometry. This transition challenges reductionist approaches to understanding. At extreme densities, the behavior of individual particles becomes less informative than the behavior of spacetime as a whole. Black holes thus encourage a shift in perspective, emphasizing holistic descriptions over microscopic detail. The unresolved questions surrounding singularities and information loss underscore the incompleteness of current theories. These gaps are not failures, but opportunities. They point toward the need for a deeper framework that unifies gravity and quantum mechanics. Black hole birth provides a natural testing ground for such a framework, even if direct access remains impossible. The role of observation in this context is subtle. Much of what is known about black hole formation comes from indirect evidence, simulations, and theoretical consistency. This reliance on inference rather than direct observation reflects the limits imposed by horizons. Yet it also demonstrates the power of scientific reasoning to extend understanding beyond immediate perception. Black hole birth also connects physical theory with measurement in a unique way. Gravitational waves, neutrinos, and electromagnetic signals each capture different facets of collapse. Their combined interpretation reveals a process that no single channel could describe alone. This multi-layered approach exemplifies how modern science tackles complex phenomena. On a deeper level, black holes challenge intuitive notions of space, time, and causality. They reveal that time can slow, paths can converge, and futures can become unavoidable. These features are not artifacts of mathematics. They are physical realities predicted by theory and supported by observation. Understanding black hole birth therefore requires intellectual flexibility. It requires letting go of assumptions shaped by everyday experience and accepting that the universe operates according to principles that may feel unfamiliar. This acceptance opens the door to deeper insight. As knowledge grows, black holes shift from being symbols of mystery to being tools of understanding. They test theories, constrain models, and illuminate extremes. Their birth, though hidden, informs much of what is known about the universe's structure and behavior. In this sense, black hole formation is not only about collapse, it is about revelation. It reveals how gravity behaves when pushed to its limits. It reveals the boundaries of matter and measurement. It reveals the deep connection between geometry and physics. As we approach the conclusion of this exploration, the birth of black holes stands as a reminder that the universe is governed by consistent laws, even in its most extreme manifestations. These laws produce outcomes that are both elegant and profound, shaping the cosmos across vast scales. The story of how a black hole is born ultimately reshapes how the universe itself is understood. What begins as the death of a star or the collapse of dense matter becomes a lesson about the structure of reality. Black hole birth shows that the universe does not resist extremes indefinitely. Instead, it allows processes to run their course until fundamental limits are reached. And when those limits are crossed, space-time reorganizes itself accordingly. At its core, black hole formation reveals that gravity is not merely one force among others. It is the architecture upon which all motion unfolds. When matter collapses into a black hole, gravity is not acting on space-time. It is space-time. The distinction between object and environment dissolves. The black hole is not something embedded in space. It is a region where space and time have been reshaped into a new configuration. This realization alters the meaning of cosmic violence. The birth of a black hole is often associated with destruction, yet it is governed by order rather than chaos. The equations describing collapse are precise. The outcomes are predictable. What appears catastrophic on a human scale is, on a cosmic scale, an orderly transition between states permitted by physical law. The quietness of black hole birth is especially revealing. Once the event horizon forms, the most dramatic part of the process becomes observationally silent. There is no final flash or signal announcing completion. The universe simply continues, now containing a region forever hidden. This silence is not emptiness. It is structure without visibility, consequence without direct witness. Black holes also teach that absence can be as informative as presence. Astronomers identify black holes by what is missing: light that never arrives, matter that vanishes without surface interaction, stars that orbit nothing visible. Black hole birth leaves behind gaps that must be explained, and those explanations consistently point toward collapse beyond recovery. The universality of black hole formation reinforces the idea that the universe is governed by thresholds. There are boundaries that cannot be crossed gradually. When pressure fails beyond a certain point, collapse becomes absolute. When escape velocity exceeds light speed, horizons form. These thresholds define phases of reality, separating the possible from the impossible. These phase changes are not unique to black holes, but black holes represent the most extreme example. They show how the universe enforces consistency, rather than allowing contradictions, such as infinite compression without consequence. The universe resolves extremes by restructuring space-time itself. Black hole birth also reveals the interconnectedness of physical scales. The collapse of a stellar core influences galaxy evolution. The formation of horizons affects cosmic entropy. The behavior of matter at subatomic scales determines outcomes visible across millions of light years. This connectivity emphasizes that no scale operates in isolation. The study of black hole formation further demonstrates the power of inference in science. Much of what is known comes not from direct observation, but from consistency across theory, simulation, and indirect evidence. This approach reflects a mature understanding of how knowledge can be constructed even when direct access is impossible. As detection methods improve, this inferred picture becomes increasingly detailed. Gravitational wave astronomy provides confirmation of collapse pathways. Observations of stellar populations refine mass thresholds. Studies of galactic centers illuminate early black hole growth. Each advance adds resolution to a picture once dominated by speculation. Black holes also redefine what it means for something to end. When a star collapses into a black hole, it does not simply disappear. Its mass, angular momentum, and influence persist. The star's identity is transformed, not erased. Black hole birth is therefore a transition, not annihilation. This transition has philosophical implications. It suggests that endings in the universe are often reconfigurations rather than terminations. Matter changes form. Information changes accessibility. Structure changes expression. Black holes exemplify this principle in its most extreme form. The inevitability of black hole formation under certain conditions also reflects the impartiality of physical law. Gravity does not make exceptions. It responds only to mass and energy. When conditions are met, collapse proceeds regardless of scale, location, or context. This impartiality gives black holes a universal character. Understanding how black holes are born therefore deepens appreciation for the coherence of the universe. Even in its most extreme phenomena, nature follows consistent rules. These rules may challenge intuition, but they do not contradict themselves. As this exploration nears its end, black hole birth stands revealed not as a singular mystery, but as a window into fundamental reality. It exposes the structure of space-time, the limits of matter, and the reach of gravity. It connects stellar death to cosmic order, collapse to geometry, and silence to meaning. The birth of a black hole ultimately serves as a lens through which the universe can be understood more clearly, and it reveals not only how extreme objects form, but how nature resolves its deepest tensions. Gravity and pressure, order and collapse, visibility and absence all meet at the threshold where a black hole is born. What emerges from that threshold is not chaos, but a new and stable configuration of reality. Understanding how a black hole is actually born dispels the idea that these objects are anomalies or disruptions. Instead, they are lawful outcomes, produced when familiar processes are carried to their logical conclusion. Stars form, burn fuel, and die. Matter resists compression until it cannot. Gravity responds consistently at every scale. When resistance fails completely, space-time reorganizes itself into a form that preserves coherence. The black hole is that form, and this perspective reframes black holes as participants in cosmic balance rather than symbols of destruction. Their formation removes excess mass energy from unstable configurations and locks it into long-lived structures. In doing so, black holes help regulate galaxies, shape large-scale structure, and influence the flow of matter across cosmic time. Their birth is not merely an ending, but a stabilizing event in the broader evolution of the universe. Black holes also teach humility about the limits of knowledge. Their interiors remain inaccessible, not because of insufficient technology, but because of the universe's causal structure. This boundary reminds us that physical laws define not only what happens, but what can be known. Yet within those limits, understanding continues to expand. By studying horizons, waves, and surrounding motion, insight grows without violating fundamental constraints. The story of black hole birth highlights the power of indirect observation. Signals that fade, motions that persist, and ripples that propagate all carry information about events that cannot be seen directly. This method of learning reflects a broader truth about science. Reality does not need to be fully observable to be comprehensible. Consistency, prediction, and coherence provide reliable guides. At the same time, black holes remain signposts pointing beyond current theory. Singularities, information loss, and quantum effects at horizons mark places where understanding is incomplete. These gaps are not failures. They are indicators of where future discovery will occur. Black hole birth thus functions as both confirmation and challenge, validating known physics while demanding deeper frameworks. The endurance of black holes across immense timescales reinforces their importance. Long after stars fade and galaxies quiet, black holes persist, carrying the mass and history of earlier epochs. Their formation shapes not only the present universe, but its far future. In this sense, black hole birth connects beginnings and endings across cosmic duration. Perhaps most profoundly, black holes change how reality itself is perceived. They reveal that space and time are not static backgrounds, but dynamic entities capable of transformation. They show that silence can contain structure and absence can convey information. They demonstrate that extremes do not break the universe, but reveal its underlying order. And to ask how a black hole is born is to ask how the universe behaves when pushed to its limits. The answer is not violence without rule, but inevitability governed by law. Collapse follows principle. Horizons form by geometry. What cannot escape does not need to be destroyed. It simply becomes unreachable. In the end, black hole birth is a story of transition. Matter becomes geometry. Motion becomes curvature. A star becomes a region of space-time with its own causal boundaries. This transformation is one of the most profound processes in nature, not because it is dramatic, but because it is consistent. By understanding how black holes are born, understanding of the universe deepens. Gravity is seen more clearly. Matter's limits are revealed. Space-time's role is clarified. The cosmos emerges not as a collection of isolated phenomena, but as a coherent system governed by principles that hold even at their extremes. This is why black holes matter. Not because they consume, but because they reveal. Not because they destroy, but because they define. Their birth is the universe explaining itself in its most uncompromising language. And in that explanation, silence is not the absence of meaning. It is where meaning becomes permanent.